everybody, and thank you very much for coming. There's some more seats down the front here if you can't find them at the back. So I'm Jo Haigh, and I'm a professor of atmospheric physics here at Imperial, and it's great to see so many people turned out on this very cold day. And I'm going to talk to you about climate change with my wonderful helpers over there, Simon and Chris and Kelvin, and they've got all the dirty work to do, and I just stand here and look important. So, you know, we'll see how we get on. So I'm talking about climate change, and what do we mean by climate change? Well, you'll often hear people talk about global warming, so that's one measure of what you might call climate change, is how much the surface temperature of the Earth is changing. And you can see in this picture, which actually has 3 different data records on, and that's the global average surface temperature across the globe from 1850 to very, very recently. And you'll see it's wobbling around all over the place, but overall it's going upwards. And this is really what's called global warming. One important thing to notice is when you see these graphs, they always have different offsets. So, for example, this one, the 0 line is I think it's the 1950 to 80 average or something like that, I can't remember, but you can see 1961 to 1980 average. But of course, when people talk about degrees of warming since pre-industrial, it's actually from longer ago. So you see, if you look at the 1850 to 1900 average, then the surface temperature now is about 1 degree warmer than it was then. And you might think, oh, well, 1 degree, you know, so what? 1 degree warmer yesterday than today or something. But 1 degree over the globe is actually quite significant, and we'll see why, I hope, soon. So today I'm going to talk a little about what are the factors influencing climate, a few measures and observations of how climate's been changing, a little bit about how we use computer models to study the climate and how it's changing, and then look at what's happening in the future and what we might be doing about it. So this is a bit of a cartoon about what actually determines the Earth's temperature. So here we've got the sun and the Earth. Sorry, my graphics are a bit crude and not to scale, obviously. And there's the radiation coming out of the sun, and all the energy driving the climate system is coming from the sun. There's not any energy coming from anywhere else. The amount of heat coming out of the core of the Earth is absolutely tiny in comparison. So that's all the energy that's driving the climate system. Then, of course, the Earth gets hot, and it emits heat radiation to space. And that's very simple to work out. If you know how much of the sun's radiation is coming in, you can work out what the temperature of the Earth would be in order to radiate out that back to space, and you work out that it comes to minus 18 degrees Celsius. So you think, now that's a bit of a problem. She's obviously got something wrong there then, minus 18. We know it's not minus 18. But of course the issue is, what we're talking about is the radiating temperature and not the actual temperature at the surface. And here we have to consider what's called the Earth's energy budget. Now, this looks a bit complicated, but it isn't really. The yellow radiation here is the stuff that I showed you, the energy coming out of the sun. And about 30% of that is just scattered straight back to space, so that's not doing anything to heat the place up. About half of it gets to the ground, and it heats the ground. And the ground gets hot, and then these red arrows here represent the heat radiation. And so the heat radiation is coming out of the Earth, and a large proportion of that is absorbed by the atmosphere and clouds. So the atmosphere is a material, it gets hot, and it radiates heat in all directions, downwards and upwards, and that's the greenhouse effect. But let's have a look a little bit more at the reflectivity of clouds and the radiative property of clouds. So we're now going to have a cloud, I think. It's going to appear. Is somebody doing the infrared picture? Yes. Yeah. So it's got some dry ice here, and it's going to pick up the little water droplets and make a nice little cloud, she says, hopefully.
My scissors.
You forgot his scissors. Oh, we're such high tech here in Imperial College.
Yeah, science and technology. Has anyone got any keys? Sorry.
put them in my pocket. Things have gone. The one thing we need.
Aha.
The office key is very useful.
Well, if you can't do that, get him to do it. Yeah.
So hopefully, as we add our dry ice, which is about minus 90,
Yeah, after he's done.
you can see a cloud forming.
Right, so that's lots of tiny little water droplets are forming. And it should turn into a nice cloud. Now, of course, the cloud is white and bright. It's reflecting the light back to your eyes, so it looks white. And that's exactly the same as the cloud in my picture up here. It's reflecting the sunshine back to space because it's reflective. But it's also very cold. So if we look at that using the infrared camera, can we do that?
Oh, it says cooling. It's not. I'll try and set it to the right. No.
Oh, that's a shame.
Is this working?
Well, you managed to turn it off.
Well, it says it's HDMI selected. Should it come over? I don't know what's going on. It says it's
It's on that screen over there.
cooling. It's shut down for some reason. Oh well, sorry.
But it's not on.
No. I don't know, the projectors have gone off. I don't know why.
Sorry, Mr. Technician, we need some help.
No, it's not that. The projectors, for some reason, have gone into cooling. I think they've been on so long that they've shut down. The projectors are cooling? Yes, it just says cooling. Well, I think they've got, have they been on all day? We might need to continue with that. It's fine.
Sorry about this, everybody. Well, perhaps I'll just carry on talking about the greenhouse effect. So we can see that what the greenhouse effect is, it's a trapping of heat radiation near the Earth's surface by the atmosphere. So what happens is the sun's radiation comes through, half of it comes through, but 90% of the radiation that's getting emitted from the surface gets absorbed by the atmosphere. So the greenhouse effect, which is warming the climate, is just due to the properties of the gases that are in the atmosphere. And the gases just happen to be transparent to sunshine and opaque to heat radiation. So there's lots of greenhouse gases in the atmosphere. The most important one is actually water vapour. So quite naturally occurring water vapour is the most important greenhouse gas, and that's the one that is causing the surface temperature to be something like 30 degrees warmer than it would be. I had a minus 18 degrees Celsius, you remember, over there. But the fact that the surface is a nice, warm, equable place to live in is mainly because of water vapour in the atmosphere. But the next most important greenhouse gas is carbon dioxide. Again, perfectly naturally occurring. It's coming out of volcanoes and it's cycling between plants and the air. So there's carbon dioxide in the atmosphere, and that's the next most important greenhouse gas, and that does about a third or half as much as the water vapour. So that's very important. And the fact about human activity is that we can increase the amount of carbon dioxide in the atmosphere, but we can't really increase the amount of water vapour, not directly, because if you try and put more water vapour into the atmosphere, it just turns into rain and falls out. So it's controlled by the temperature rather than the other way around. So we need to consider all the gases in the atmosphere. There's the two most common ones, of course, are nitrogen and oxygen, but they are completely transparent to most sorts of radiation. So the sun's radiation comes straight through them, and the heat radiation goes straight through them as well. So although they're the most common greenhouse gases, the most common gases on the planet, they're not acting to affect the temperature. So we have a number of other gases. The next one, after greenhouse gas after carbon dioxide, is methane. And that's, of course, naturally occurring, but it's also influenced by human agricultural practices, in particular through ruminant animals, which, are releasing methane. And if you have more agriculture with more cows, you increase the amount of methane in the atmosphere, which again will increase the greenhouse effect. How are we doing?
Hopefully we're back on. Yes.
All right. Shall I just carry on the talk then?
Yes, sorry.
Okay. I think we've given up on the... Oh, right. Something's happening. Yay. Right, apologies for this.
I think we leave it like that. Leave it like that. Okay.
Right, I think we stopped looking at the cold cloud anyway.
Yeah, sorry.
Okay, right, thanks. So a change in any of those radiation streams will affect the surface temperature. So if reflection by clouds, that was that, and by greenhouse gases. So I've just mentioned this. So the most important greenhouse gas is water vapour, but the one that we can influence is carbon dioxide. So how much carbon dioxide is there in the atmosphere? I'm now going to show you lots of little graphs, which looks a bit techie, but there's quite a good point to these graphs. And what we've got in each of them is a sort of time series, and you can see this one is millions of years ago, and the amount of CO2 in the atmosphere. So millions of years ago, you can see there's vast amounts of CO2 in the atmosphere, and you can see there's a little red bit at the bottom. It says 0.04%. That's how much we've got today. So a very, very, very long time ago, there was more CO2 in the atmosphere than there is now. So it's all natural then, is it? Well, of course, but we've got to put this in context. The first primates didn't appear on Earth until 3 million years ago. So life as we know it today hasn't existed in concentrations of CO2 anything like as high as that. So we're now looking at different graphs of different time periods. This one is hundreds of thousands of years, and you can see the 0.04% is now at the top. It's going up and down, but it's well below what it is today. We can look at modern humans who didn't appear until 200,000 years ago. So you see humans have been in these low CO2 atmospheres all the time. This is now 10,000 years ago, and the CO2 concentration is pretty much flat. You see it about this 280 of these units. And then we've got, this is now 1,000 years ago, and you can see it's pretty flat going along, 280 parts per million, until there's a little whoopsie right at the end, and that's what's happening now. And that's CO2 over the last 50 odd years, and it's just going up and up. And you can see this is just the annual cycle due to the plants and things. So if you've got all of these graphs together, what you can see is that the concentration of CO2 has been below 400 parts per million, or 0.04%, for millions of years. And life has evolved with and alongside the CO2, but it's now, we haven't had that anything like life as we know it today. And we know quite well that this increasing CO2 is coming from burning fossil fuels because we can carbon date it. So we can say it's old stuff, it's coming from fossil fuels. So we're influencing the surface temperature through increasing CO2. But what about other things? What about the sun? Now, of course, the Earth's going round the sun in a particular orbit, and the orbit has various parameters that determine it. One of them is the shape of the orbit, so it's actually not a circle, it's an ellipse. So sometimes of the year, the Earth is slightly further away, and sometimes it's slightly closer to the Earth. Sorry, we're not doing the... No, okay. Sometimes it's slightly closer to the Earth. And also there's the tilt of the axis. So we have, that determines the seasons. So we've got, over that side is the June, so that's northern hemisphere summer, and the northern pole is pointing in towards the centre. And that's the southern hemisphere summer on the other end. And the third parameter is a slight, it's called a precession of the orbit, and it's telling you where on this elliptical orbit the North Pole is pointing in towards the centre, so it's a sort of timing issue. And all of those factors are going to affect the amount of radiation and where it's distributed over the Earth. So that's going to influence the climate. Now let's go back well, let's have a look at a temperature curve. And this is the temperature of the Earth over hundreds of thousands of years. Now, you may think this curve looks familiar, and that's because I've already shown you that curve, which was the CO2. And you can see they're going pretty much in phase. So what you can conclude from that? Well, some people say, oh, see, CO2 and temperature, they've been going up and down together all the time before, perfectly natural, no climate change due to human activity, it's all natural. Unfortunately, this graph is far from reassuring. In fact, it's rather the opposite. What's happening here is that the original push on the temperature is given by this changes in the Earth's orbit around the sun. And when the temperature starts to rise slightly, then CO2 and indeed methane and other gases get released from stores in ocean sediments, in clathrates, in tundra and places, and those greenhouse gases get emitted into the atmosphere. They act as a greenhouse gas, then it gets warmer, then you get more of the gases, then it gets warmer, and you get this very sharp increase that you can see there of both the CO2 and the temperature at the same time. And then the orbital effect changes slightly and goes back the other way, so then you've got the sun's effect tending to cool it, and it very slowly goes back down again. So if you've got anything that gives it an initial push, in this case it's the sun's radiation, but it could indeed be human greenhouse gases, gives it an initial push, then you'll get this compounding effect of all the other greenhouse gases adding up and making it worse than it would have been. So far from being reassuring, this picture is actually quite worrying, although of course this is on a very long time scale compared to recent warming. So I was going to say a little bit about computer modelling. So this is actually very, very simple in concept. You just write down some very basic laws of physics and you code them up for the computer. First is Newton's second law, which some of you may remember. Force is mass times acceleration. So you're looking at a parcel of air and you're thinking about the forces acting on it, which might be gravity, or it might be some pressure gradient in the atmosphere. You've got the high pressure over there and low pressure over here, tend to push the air this way. You consider the effect of the Earth's rotation. You consider things like viscous drag and that sort of thing. That's the first equation. Second is conservation of mass. So that's saying if you've got some air and it's coming this direction, it's either going to go past or else it's going to get squashed. You've got conservation of energy, so you've got a parcel of air. If something's heating it up, it'll either get hot or else it'll expand, or both. And then you've got the ideal gas law. And my willing helpers, I hope. Oh no, he's got something dangerous looking there.
This one's low-tech.
This one's low-tech, okay. It's going to do a quick demonstration of the ideal gas law. So you'll remember it. PV is RT, you remember from school. So if you've got an amount of air, then the volume is proportional to the temperature. So he's got some balloons that have been filled up with air earlier and then put into this liquid nitrogen dur, so they're very cold. And so the gas inside that balloon will be warming up now. And so it's expanding due to the fact that it's getting warmer. Oh, he's got a third one. Oh, he's got more of them. That's a good one over there. So it's a very simple demonstration of the ideal gas law. So it's all really basic classical physics in here. And what you can do is you write down all these equations, and you end up with essentially 6 equations in 6 unknowns. And the 6 unknowns are pressure, density, temperature, and wind in 3 directions. So it can go north, south, east, west, and up and down. So you've got 6 simultaneous equations, the 6 unknowns, you can solve it. And this is the basis of both weather forecasting and climate modelling. So you solve the equations on a 3D grid, and you step forward in time, and that is essentially a weather forecasting model and also a climate model. So it's a bit like Minecraft. The younger members of the audience here may play with Minecraft, but climate models have actually much less detail. But the idea is the same, it's all very blocky. So, of course, the real world is actually somewhat more complicated than that, and if you're trying to represent like real clouds and real rainfall and real topography, it is a bit more difficult than just having this blocky thing. But that's the basic physics of what's going on. So you might say, well, actually, that's all very well, and you're saying how simple it is, but the weather forecasters can't do better than about 10 days. So how in the world do you climate people think that you're going to forecast 50 years, 100 years hence? So the answer to that question is that we're not trying to predict the same thing. So if you're doing a weather forecast, you might be saying that the weather in London next Tuesday is going to be such and such. With climate prediction, what you're saying is that the general temperature in southeast England in winter, or in March perhaps, is going to be typically this. So you're not going to do a precise forecast, you're trying to do a typical forecast for that area, larger area, and over a longer time period. So it's the same physics but used in a slightly different way. So can we explain the shape of this graph? So at the top here we've got various of these climate model simulations. There's lots and lots of spaghetti there. The black curve there is the measurement. It's the same measurement I showed you right at the beginning of the global warming, or the temperature curve. The yellow and the blue curves are these climate model simulations, and in them they've taken account of the greenhouse gases, of industrial pollution, of changes in land use, so that's surface reflectivity, changes in the sun, volcanic eruptions, and also energy into and out of the ocean. So that's all the physics we put in there as much as we can. And what you can see is that although there's not a precise correspondence between the coloured curve and the black curve, this general envelope follows the same shape. So we're predicting a typical weather, the typical climate, and it's doing rather well. And you can't match that curve without including human-produced greenhouse gases. Another important point to be made out of that is, this is a lot of spaghetti. And the different examples are all different because you start it off from a slightly different point at the beginning of the simulation, and it'll go on a slightly different trajectory, but it'll follow the same broad curve. Now, the Earth itself, of course, is not an average, it's not an envelope. It's one of those spaghettis, or perhaps none of them, but it's following the same general shape. This is just to make the point that we say global warming, but of course surface temperature is not increasing everywhere at the same rate. So in some places it's increasing a lot more, particularly over the continents. You can see there over Asia and over South America, the increase in temperature over 100 years there is getting on for 2 degrees. In some places it's hardly varying at all. So in particular, you see, interestingly, over the North Atlantic Ocean, there's been almost no warming at all. So global warming does not mean that you've got the same temperature increase everywhere. Some people feel the effects more than others. So this is looking into the future, and we can make assumptions about what the CO2 will do. So forecasting the climate is difficult enough, but you've got to forecast the CO2, which means you've got to forecast where it's all coming from, you've got to forecast the economy and everything else, which is way beyond anything I'm capable of. But you can make different sort of scenarios or examples of what might happen. So the red curve there is if you continue to increase carbon dioxide emissions as they're going at the moment from fossil fuels and all the rest of it. And the bottom curve is if you peak CO2 emissions in 2020 and then cut them off to zero by 2075. So that's quite a dramatic change in human use of energy. But what you can see from there is even if you decline them to zero by 2075, you're not getting back to the temperature that you are today because the response is very, very slow. So it's flattening off at that's about 1 degree above the temperature now, so it's about 1.3 degrees above pre-industrial, even if you do this incredibly dramatic action to decline the CO2 emissions to zero by 2075. Now, other evidence for climate change, we can look at things like Arctic sea ice. Are we doing a demonstration on this one? Oh, we are? Okay.
Hopefully, as long as I don't shut everything off.
So, what we've got here is pictures of Arctic sea ice at the summer minimum. So obviously there's an annual cycle in sea ice, and there's less in summer and more in winter. And we can look at the area of the ice in summer and compare it year on year. Now, you have to be very careful when you're comparing individual years, Oh, it's working. Hooray.
Here you are. We've got our 2 sheets here, hopefully.
Comparing individual years, so just taking one year and another, it's a bit of a risky strategy, but this is just to give you 2 examples, and you can see in 1979 a much larger area of ice there stretching over the edges of the Arctic Ocean than it was in 2011. And indeed, it's gone down by about a half over those periods, varying year on year, but that's the actual effect. Now, that is partly... Are we ready? Yeah. So it's partly a symbol or a signal of climate change, but it also has a knock-on effect on global warming, because if you have something that's reflecting the sunshine, then it's sort of cooling the planet as well. So if you make it smaller area, it's reflecting less, and it's warming more. So what we've got here now is an example, and here's some sea, and here's some ice. And we're going to look at the temperature of these things through the infrared camera. That's the left, yep. Top left up there, and we're looking with the infrared camera at the 2 boards, and you see they're looking pretty much the same temperature, but they're looking very different in the visible. So the white one's bright and the black one's dark. Now, when he shines some light on here, yep, you can see perhaps the temperature of the black one, it's all right, don't change it, is changing. So what's happening is that the black one is absorbing the energy out of these lights and heating up, whereas the white one, which is reflective, is just reflecting the sunshine back and it's not warming up. So it's a very simple demonstration of what we might call albedo feedback on the climate system. So as the ice gets less, the surface gets darker, it absorbs more radiation, and the surface heats up more. So that's the positive feedback. Good, nice demo, chaps. So the other evidence is, of course, sea level rise, and the sea level has been going up sharply very recently, and you can see that over the last, since the 20th century, it's gone up by, this is an American slide, so it's in inches, but about 20 centimetres or so. And the picture on the right there is showing Greenland covered in ice. So the ice I was showing you before was sea ice. It was ice that was floating on the surface. If you melt that, it doesn't have any effect on sea level because the water is occupying the same volume as it did before. You know, if you melt a glass ice cube in a glass of water, it doesn't change the level of the drink. But if the ice on the land melts, then it goes into the sea, and then the sea level rises. And this is a picture of Greenland up there, and this is a photograph of some ice melt flowing out of Greenland into the oceans on a particular occasion there. So the sea level rise is due partly to melting of ice on the land. So this is land ice like that, and it's also glaciers. But also, as the oceans get warmer, they expand, and then the water rises, and that again contributes to sea level rise. And this is just showing the same 2 examples I showed you before, the different CO2 assumptions. So the blue one, again, is if you're dropping CO2 emissions to 0 by 2075, the sea level rise doesn't stop, doesn't even slow down for a very, very long time. It's innate in the system. The heat is in there, and it takes a very, very long time to slow down. So we're committed to some sea level rise already. I think in the interest of time, I won't show these, but these are just simulations of what sea level might do in areas around the Thames. And this is just looking at impacts. So it's all very well talking about, you know, temperatures and large-scale things and that sort of business, and you might think, well, how's that going to impact me, or how's it going to impact humans? So the real effect, of course, varies across the globe, and some places will have too little water. So you see there, this is suggesting that by 2100, with that worst scenario, there'll be 2 billion people with not enough water, essentially. And then, of course, other people will be affected by intense storms and flooding. So that's in the middle left there. Large numbers of people are exposed to heat waves, which, of course, are bad for health, and the effects on plants and also biodiversity. So we need to stop putting greenhouse gases into the atmosphere, basically, if you're going to try and avoid all this stuff. And you'll be aware that a couple of years ago there was the Paris COP meeting, Conference of the Parties, the United Nations Framework Convention on Climate Change, which agreed to try and stop global warming to less than 2 degrees. You can't imagine what an amazing event that was. So the previous big COP meeting had been in Copenhagen about 5 or 6 years previously, and we were hoping that they might agree something. And they agreed absolutely nothing at all. It was an incredible disappointment. So in Paris, we were just hoping perhaps they might agree something, anything, please. And they came up with this unanimous, absolutely unanimous, 195 countries all agreed that we can do something about it. This is remarkable, amazing, and to try and do better. Now, that's the good side of things, but you've got to actually do it. There's no point just talking. You've got to do it as well. But, you know, one thing at a time. So I've just got to finish. I'm running out of time now. But just to say something about energy usage, because, of course, energy is a big component of all this CO2 production. And this is all the big numbers here, quite difficult to sort of gauge. So each person in England wants about 4,000 watts. England together needs about 200 gigawatts. That's a billion watts, 200 billion watts. And globally, current human consumption is 16 terawatts. That's 1,000 billion watts. There's huge numbers here. But you look at these numbers in the context of the amount of solar radiation. This is absorbed by the Earth. This is not just emitted by the sun. This is actually absorbed by the Earth energy. The numbers are huge. This is telling you something about the amount of solar energy that's available that we could use for producing energy. And so I just want to, that's about the UK carbon budgets, which are fantastic, but I haven't got time to talk about that now. And then about, so renewable energy is rising fast. This is just for the UK. It was 25% of electricity generation. Of course, electricity is not all energy that we need, but it's part of it. And things are looking good. The offshore wind, which this picture was quite recently, but the offshore wind is growing apace, and it's now 25% of, or aiming to be 25% of the electricity by itself in 2020 for the UK. So things just grow faster and faster. It's sort of much faster than we could have anticipated. And in the UK, it's going to be mainly offshore wind, possibly more onshore wind, and also solar, even though we're not the best place in the world for sunshine. So just to finish off, action on climate change. It's not for me to tell people what to do, but here's some possibilities that you might like to consider. Everybody's different. Everybody's got to do their own thing. But saving energy seems to be quite a sensible thing to do anyway, because it'll save you money as well as saving the planet. And there's some other examples on there. Eating less meat is a good one, and I'm not telling everybody they have to be vegetarian and everything, but it's far less efficient to grow crops to feed an animal and then eat the animal than it is just to grow the crops and eat the crops. So I know that all sounds very boring, but you know, think about it a bit. And I'll leave it there. Thank you. So happy to take any questions. There's one at the back. So we can't hear. If you stand up and shout, yeah.
What's the toughest research problem today in climate science?
Oh.
Potentially you could solve in 10 years' time with quantum computing, because there will be more opportunities to do more advanced modeling.
Yes.
So there's something that potentially you could solve then that could also tie into electric physics.
Yes.
Climate change.
So the question is, what's the most difficult science in climate change? Now, it depends what you incorporate in climate change. If you include all those impact side of things and flood forecasting and all the rest of it, that's hugely difficult. But if I just talk about my own area, which is the sort of physics of climate change, then the really challenging thing at the moment is looking in more detail at the response of clouds. So as we tried to demonstrate, clouds are very, very important in this radiation budget. So, for example, if you've got more clouds in the atmosphere in response to climate change, they might cool the planet by reflecting sunshine to space, or if they're lower down, they might make it worse by trapping the heat radiation. And we're only sort of in a very general sense, understanding these at the moment. So if we could actually pin that down, that would also narrow the range of warmings that we'd get predicting into the future. Yeah, at the front.
Speak up properly.
I can repeat the question.
Okay. Within the context of CO2 generation and man-made climate change, some scientists talk about the zone of irreversibility, the point at which we can't quickly enough reduce the amount of carbon dioxide there is in the atmosphere. Could you talk in a bit more detail about that and tell us what your thoughts are?
So the question is about if a zone of irreversibility is the phrase, but it's a sort of tipping point question. Is there such a point that it gets so bad that you can't then do anything about it? So the 2 degrees, which was specified by the Paris Agreement, was set up as perceived to be what would be called dangerous climate change, which I think means all these impacts on the ways people live. But I don't think it's quite the same thing as this tipping points. Now, tipping points are things like you melt all the ice over all the continents, and particularly over the Arctic and the Antarctic, and that all melts into the sea, and the sea level rise goes right up, and you can't get the ice back again. That would be a tipping point. Or you do something with biodiversity to remove most of the plants, and then you haven't got all the basis of the food chain and all the rest of it. I think those things are quite a long way off. We're not getting anywhere near those things at the moment, but certainly, if we could try and keep things under 2 degrees, it would be better. Yes, at the front over here.
Why did the dry ice stop making a cloud?
He says, why did the dry ice stop? Stop making a cloud? Because there was a certain amount of cooling material and it just warmed up. So yeah, over there.
How did you get the data for the amount of CO2 back in 10,000 years ago and 1,000 years ago?
So there's all sort of different ways. I mean, I don't do it personally. There's very clever people can do it. So one way, for example, is if you look in ice cores, if you drill ice cores into the Antarctic, you get all sorts of records in there. And one of them is a record of the composition of the atmosphere that was when that snow was laid down. So you can actually deduce how much CO2 was there then. You can also look in other records, like in lake sediments and in old rocks and things like that. Will give you these sorts of. So very careful, clever people do these sorts of very, very, precise measurements. In the middle.
What's your opinion on carbon capture and storage?
So the question's about carbon capture and storage. So this relates to what we're going to do about reducing the carbon emissions. And even if we try as hardest as we possibly can to release as little CO2 into the atmosphere, we're going to be releasing some. So the question is, can we get some of it back out again? And one way that is carbon capture and storage is where you suck the CO2 out of industrial emissions, and then you make it into some sort of solid form, and you bury it somewhere forever, perhaps in some sort of geographical stratigraphy. So it's possible. In fact, we've got a demonstrator plant in the chemical engineering department here to sequester the carbon out of the air, but it's not been demonstrated that anywhere that it can really be done at scale. I mean, as examples, I think the Norwegians have, they're doing this from some of the burning of the oil that they do, and they're getting the CO2 and they're pushing it back into where the oil came from, so it sort of seems to be quite efficient. But it's not been demonstrated at scale. It's not been shown that we can do it enough. And also, the very idea that we might be able to do that somehow gives people a sort of legitimization for not doing as much worrying about what they should be worrying about, which is the cause. So I think it's technically something we may have to implement, but I don't think it's a sort of, the golden bullet. Yes, at the back. So I don't know anything about ancient Greeks, I'm afraid, but I do know that, of course, there's been climate change in the past, and particularly, I don't know about ancient Greeks, that would be like several thousand years ago, wouldn't it? I mean, if you go about to the year 900, it was certainly slightly warmer then than it has been more recently, and certainly there's been passages through those sorts of areas, but I don't know much more about it than that. I mean, we've got the temperature records that show the global average temperature back then is probably lower than it is today. The thing about today is when people argue about whether it was warmer then than it is now, it's probably warmer now, but even if it wasn't, what we've got now is an incredibly fast rate of increase. That is faster than anything we've seen. It's faster than coming out of the ice ages. It's scary fast, you know. So even if it was the case, and I don't know, that it was warmer in the past, recently a little bit, then that's not an excuse not to do anything. Sorry, I can't hear. Yes, just in front, yeah.
I'm not a climate change skeptic or anything, but there is sort of an argument that we're getting better and accurate at measuring these things. We've got more places where we're measuring them, and you showed a very interesting graphic which showed that it's not even across the entire planet.
Yeah.
You know, how much is the argument, the skeptical argument, in that maybe those hotspots are just moving around and we're sort of experiencing anomalies of a pattern? I know that it's but I suppose to knock the skeptics on the head. You know,
Well, I don't want to knock anybody on the head. I'm not interested.
But that is their argument.
I'm not interested in having personal, you know, vendettas or anything like that. We've got to look at the science, and we've got to do it objectively and use the data. And there are people, rather in the same way as I was talking over there, whose job it is to analyse the temperature records and all the temperature records they can get. For the more recent ones, for example, you know, you can use other sorts of records like tree rings and all these sorts of things. And they do it over the globe. Since 1850 or so, we've actually had thermometers, not evenly spaced all over the globe, of course not. But they collate all those sorts of records. They take into account things like, obviously, if you've got a city, it'll be hotter than around the outside, so you must take account of that effect. That's not the actual atmospheric warming, that's just local industry or something. So it's not easy. And the plot that I showed right at the beginning, which was the coloured curves of temperature increase, but it had the grey band around it. That grey band is essentially a range of uncertainty, and that's taking into account all these, you know, uncertainties in each of the measures. But of course, when you collate all those into a global data set, that sort of concentrates it a bit. So it's certainly not easy. I didn't go into detail on that plot I showed you with the, you know, some places warm and some places not so warm. You might have noticed that there were little crosses on it. The little crosses were places where you can sort of probably be statistically sure that they're right. And where there weren't little crosses, the uncertainty is too large. So when I said that it's cooler over the North Atlantic, that was slightly naughty because there weren't little crosses on the North Atlantic. But my point was just that it's not the same everywhere. It tells you all sorts of interesting things about the change in climate, of course, is not just global warming, it's changing in circulation. So the thing about the cooling in the North Atlantic may be due to changes in ocean circulation. The things where it's warming over the continents may be due to different changes in the overturning circulation of the atmosphere. And the computer models, of course, can look at all these things and try and see what the physics is telling you. Yeah.
What's your interaction with the government?
What's my interaction with the government? I've been a lead author on the Intergovernmental Panel on Climate Change reports that come out, big reports that come out every so often. I guess that's sponsored by the government. I've received research grants from government research councils. And I suppose as an employee of a university, I'm a government employee as well. Is that what you mean?
I just want to see how much of an influence on policy.
Ah, right, okay, so it's the other way around. So, absolutely. So, when we're doing all this science and all the climate predictions and everything, we're trying to make sure that everybody can sort of get access to that information and try and interpret it in the way that they will find useful. So in the Grantham Institute, we have somebody who's called our Director of Policy and Translation, and her job is to translate the scientific results into a way that's useful for policymakers and indeed the general public and anybody else that wants to know. Yeah, thanks. Piers, hello.
Hello. Yes, just Joanna. I think the main problem you've got though is that the actual observed data shows that carbon dioxide levels are an effect, not a cause of temperature in climate. And at the same time, we've had all the extreme scare story predictions of the United Nations have been proved wrong. They said we were going to see the end of snow and less and more hurricanes in America. We've had the opposite. And as for the rate of increases of temperature, there's actually a 60-year cycle in rates of increases of temperature and 60 years.
Right, that's 3 questions. Thank you.
Well, it is.
So in
and now to the last question, when are you going to give up this spurious theory and end wind farms which are killing birds?
Piers just doesn't believe the physics of the greenhouse effect, which is very sad because it's very, very fundamental. The observed fact of CO2 following the temperature, I showed you precisely on the 100,000-year temperature cycle of the things. The CO2 that's increasing now is very much coming from human activity and the physics of the greenhouse effect. There's no point arguing with him because he won't listen to the physics. What was the second question?
I'd like to hear our answer, please.
What's the second question? I've forgotten.
Well, I was just saying that the reason for the increase now is a delayed effect from the medieval warm period through the ocean.
Of course there's a lag through the oceans. Indeed, overturning circulations in the oceans are very, very slow to respond. But all the models that include these sorts of things...
I want evidence that CO2 is doing that. There's no
the evidence is that if John Tyndall back in 1880 could show you what the physics of a greenhouse effect is. We've got the physics in the models. We can't do any of the simulations without the human induced greenhouse effect. You try and show me that it's not.
Yeah, I can do it.
Okay, good. I'll look forward to your scientific paper in a peer-reviewed journal, then we will read it and take it with some interest. Thank you.
Loads of peer-reviewed.
Any more questions?
Peer-reviewed papers that destroyed the CO2 thing.
You got a question? No? Yeah.
Do you also study the effect of the nitrogen cycle? I mean, the alteration of
Yes.
the nitrogen
Yes.
cycle?
So the question is about the nitrogen cycle. So, I mean, I'm not a biologist, so I'm not really very competent to speak about this. But we've got to take into account all the biogeochemical cycles, particularly, obviously, the carbon cycle is an important one, but the nitrogen cycle too, because that's fundamental to plant growth. Now, what we're seeing at the moment is, as you'll be aware, with insectageddon and all this sort of thing, that's probably due to too much use of pesticides and that sort of thing in crops. But there may be a climate change component that's causing or introducing global biodiversity loss as well. So the whole biological side of things is really very, very important. There's people who do these biogeochemical cycles and try and put them alongside the climate models, but of course it gets very complex. But it's not ignored.
Just another question. Does your department do that side of...
So I work in the Grantham Institute, which is a climate change unit. There's people in the life sciences department and also in the physics department who are doing biogeochemical cycles, yes. Yeah.
Is there a cut-off point of human extinction for temperature change? You showed the 100,000-year cycle and said humans started when it was 0.04%. Obviously, before that you had dinosaurs or whatever it was.
Yeah.
Do we have a kind of a rough...
I'm afraid that's a question for a medic. I don't know. I mean, I know, you know, if you look at those temperature increases that are predicted over the next century, the temperature rises, say, in Africa, are so large that we know that those are temperatures under which people cannot go about their normal business outside. I mean, you know, you can barely walk, let alone do anything else. So, I mean, I'm afraid I don't know that, but obviously the hotter it gets, the greater a stress it is.
From like COP and everything, everyone looks at like 2100 and the 2-degree climate change. Have you kind of extrapolated beyond that if we don't kind of make changes to why it could be in the century after that and the century after that?
Absolutely, and I think, if you don't do anything about it, it just gets hotter and hotter. I think, a key message, actually, is you may say you don't mind it being 2 degrees, you think 2 degrees isn't too bad. You may say you don't mind it being 5 degrees. I think that'll be a bit serious, but never mind. You may even have a target of 10 degrees. Whatever target it is, if you've got a target, you've got to stop CO2 emissions at some point. Because if you don't stop them, it'll carry on warming. So if you want to have a lower target, you've got to stop them soon. If you fancy a higher target, you can stop them later. But one way or the other, you've got to stop them. So you might as well start thinking about it now, she says, pedantically. Okay, I think perhaps I've gone on probably longer than I was. Oh, somebody just... Okay, last question.
Do electric cars actually help reduce the speed of global warming? Because the electricity for the cars must come from somewhere, and I saw that most of the electricity came from fossil fuels.
Yes, very good question. So the question is about energy sources and whether or not the use of electric cars helps, because the electric car needs to get its energy from somewhere. The batteries, where's it going to get the electricity from? It might be getting it from a fossil fuel source. So there's sort of two answers to that. One is that electric cars tend to be more efficient and lighter, so actually you're just using less energy, so that's a good start. But the second thing, of course, is that we need to make sure that there's electricity available to power these cars or anything else that we need from renewable sources. Is that good enough? Thank you very much. And thank you.